Hi, my name is Austin Cox and this is homework 2. Today we are going to be discussing van der Waals equation of state. And we use this equation here when gases are not ideal, and we use this in the cases where we can't use PV equals nRT. So what we have here is pressure equals R times the temperature over volume minus B minus A over V squared. So we use this equation here when on our pressure volume diagram, when we have sort of like a curve like this in which it has an inflection point at the critical temperature and volume, and normal ideal curves would be up here. So what we're looking for is this point here where we have the inflection point, where the first and second derivatives of this equation are set equal to 0. So in this equation, the volume here is our specific volume, and it is the volume in which the molecule at 1 mole. So using this equation, we're going to find the derivatives and set them equal to 0. So starting off, we can take dP dV is equal to negative RT over VC minus B squared. And then it is going to be plus 2A over V cubed. So the equations that we form here will be used to solve for our A and our B constants. So taking our second derivative gives us dP, or d squared P over dV squared, and that is going to be equal to 2 RTC, and this is also at our critical temperature, so we're just reiterating that and here. So we have 2 RTC over VC minus B, and that's going to be cubed, and then it's going to be minus 6A over VC to the 4th. So what we're going to do from here, we're going to set these equal to 0 to solve for the values of the critical volume and temperature at the critical point of a non-ideal gas. So to start, we can start with the first derivative, and that is 2A over VC cubed is equal to RTC over VC minus B squared. So once we get that, we can take our second derivative and make it 2 RTC over VC minus B cubed minus or equals 6A over VC to the 4th. So once we get to this step, we can multiply the first derivative by the inverse of the second derivative. And from this, we are going to get this times this gives us 2A V C to the 4th divided by, that is going to be divided by 3A VC. Okay, so once we evaluate our first and second derivatives at the critical points, we obtain these equations here, and then we will multiply the first derivative by the inverse of the second derivative. So this will give us 2A VC to the fourth over 3a VC cubed, and that is going to be equal to RTC times VC minus B cubed over VC minus B squared times RTC. So once we get set up here, we can go ahead and simplify and like massage this equation in order to solve for our A and B constants in which we are looking for. So here we can cancel out the A and we get 1 power of VC, and then these cancel and that cancels with those. So then we are left with 2/3 VC is equal to VC minus B. So from here we are able to solve for B. B is equal to, so we're going to add this over here and subtract the 2/3. So B is equal to VC minus 2/3 VC. And then this will give us B is equal to VC over 3. So from there, we can plug B back into our equation to solve the value for A. So we can do that over here. We're going to take our critical pressure is equal to RTC over VC minus VC over 3 minus, and we plug that in for our B, minus A over V squared. So once we get set up here, we're going to further evaluate this to solve for our A constant. So continuing on from after we solve for our B value, we can go ahead and plug this into our first derivative to solve for A. And we can do that as RTC over VC minus VC over 3 squared is equal to 2A over VC cubed. So from here we can do some simple algebra to further evaluate and solve for our A value. So we will be getting RTC, we're going to multiply this VC cubed over here, and VC minus VC over 3 is going to give us 2/3 VC, and this is going to be squared, is equal to 2A. So our 2/3 here squared is going to give us 4/9, and we're going to want to move that into our numerator, so we're going to be flipping it, and it's going to be 9/4, so we can show that as 9/4 RTC, and we have VC squared on the bottom here, and that's over on top is VC cubed, so that'll simplify to just VC, and that is going to be equal to 2A. And then to get A by itself here, we're going to divide by 2, and this gives us 9/8 RTC. VC is equal to A. So once we get our A value, we can plug this back into our van der Waals equation of state to solve for our critical pressure. So we get, I'm just going to wiggle this in here. We get our critical pressure is equal to RTC over VC minus our B value, which is VC over 3 minus our A value, 9/8 our TC VC, and that's going to be over VC squared. So once we get that, we have our A and our B's plugged in, and we are able to simplify this all the way with just our critical temperature and our critical volume and our R value, which is the given constant, to set that equal to our critical pressure. So simplifying this, we get RTC over 2/3 VC minus 9/8 RTC, and we can cancel this power, and we are left with just VC on the bottom. Moving forward, we are going to move this 2/3 that's in our denominator, and we're going to take the inverse of it, and we are going to get 3/2 RTC over VC minus, and we're going to move this 9/8 in front, RTC VC. And from here you can see that these two terms here have this RTC over VC multiplied by them. So this gives, we can factor this out, so we get P equals RTC over VC times 3/2 minus 9/8. And then we're going to simplify this, and we will get P is equal to 3/8 RTC over VC. And here, our 3/8 is our compressibility factor, which is Z for our equation. And that is because it is the value for the compressibility factor for the any unideal gas. So if we get this value here, we are able to solve for any critical temperature, critical volume, and critical pressure. If we were given any two of those, we can solve for the third unknown. This is homework 2, part A3, when we are generating pressure volume diagrams for water over the temperature range of 275 to 900 kelvins with 25 Kelvin increments using van der Waals equation of state. So to start, we can go to Google Colaboratory, and we can import our libraries, and we're going to import NumPy as NP, and then we are going to need to plot stuff. So from plotly dot subplots, we are going to be importing make subplots. Shift enter. So from here we can now input our constants, and our R for water is 8.314, and then our critical temperature of water is 647.096 kelvins, and we can just show that that's in kelvins. And then our critical pressure is equal to 22.064 E to the 6, and that is pascals. Shift enter. Next, we can go ahead and define our van der Waals equation of state, and that is, we're just going to go V, D, W of our pressure and that its parameters are going to be volume and temperature. And we can go ahead and return our equation that's over here. So we got return, we're going to go R times T, divide that by V minus B, and that's going to be subtracted A over V plus E times B, and then we're going to go times V times V plus A, or we're going to make this V plus E times B times V plus S times B. So we went ahead and returned our equation. Now we can go back into here and we can input the other variables that are not right here. So for our A, which is right here, we're going to make A equal to, and this value of that is 27/64. So we have A equals 27/64. We have the 27/64, and we're going to multiply that by R squared times TC squared, and then divide that by our critical pressure. So that's our A. And then our B is going to be 1/8 equal to 1/8 times our R value times our critical temperature, and then lastly divided by our critical pressure. So from here we have our R, our B, and our A. So what we have left is our E and S value. And as you can see here, for van der Waals equation of state, those are going to be set equal to 0. So if we wanted to, we could do this differently, where we could code it for any equation of state, but for this we're just going to hard code it in as E equals 0 and S is equal to 0 as well. So from there we can go Shift Enter. So from here we are now going to create an array of different volumes, which we could then use to put into a graph and then plot all of those points. So we are going to set V equal to NP dot log space, and we want our intervals to be spaced evenly, and from the homework we need the range of 275 to 900, but that's for the later graph. Here we are just creating the array, and our array is log based, so we can go np dot log as base 10, and we want those values ranging from 1.01 times b, and we want this ranging to -1 with 1,000 intervals. So we can go ahead and check that. Oh, I think I need to include our B outside of that. Shift enter, shift enter, shift enter. Okay, so now we can go ahead and see what our array looks like. So as you can see here, we have our array with all of our values that we needed. So now we can go ahead and hide that. And we can go to start plotting this now. So we can go fig is equal to make subplots. And then for this assignment, we're looking for diagrams of water over the temperature range of 275 to 900 kelvins with 25 Kelvin increments. So we are going to go for T in np dot arrange, and that's going to use the values on top and below of our critical values in order to plot them in the manner that we want them to. So now we are going to input our parameters, which were 275 Kelvin to 900 Kelvin with 25-degree increments. So now we are going to add our scatter plot to our program. So we can go fig dot add underscore scatter, and our x values here are going to be our array of volumes. Our y is going to be our van der Waals pressure equation with our volume and temperature as our parameters. And then next we're going to make the mode equal to lines, because we would like to plot them as lines on our diagram. Next we are going to give our diagram a name, and we're going to use an F string to enable our temperature to be manipulated in the way that we would like it to be. And we can go ahead and put a K for Kelvin. Next, we need to update our X and Y axes. So when we update our axes, we can go outside of the for loop, and we can go fig dot update. We're going to go X axes, and then we're going to make that type equal to log. So that's making our x-axis logarithmic to make our graph look more easy to read and more interpretable. So now we're going to update our y-axis. Y-axis. And for our y-axis, we are going to make our range equal to 1e to the negative 7, and then 1e to the 8. So after we have our x and y axes updated, we can then update our layout of our diagram that we are producing. So we can go fig dot update layout, and here we are going to be constricting the size of our diagram. So we can make our width equal to 800, and we're going to make our height equal to 600. So once we get all of our updates that we needed for our diagram, we can go ahead and hit Shift Enter. And we generated this diagram, and we can see here around these points here, you can notice the inflection point, and that is where we are looking for the values of the critical temperature and critical
pressure. Thank you.